All right, so topic 20 study group, last one of the phase. We're going to start with reviewing some of our regression outputs. So here, I actually just copied this from our last study group. Our miles per gallon, actually, let me just clear all of this first. Our miles per gallon data set. This one has a bunch of random transformations being done. And with that, we have our summary. So here, just an example again, we have our R squared. Again, very important to remember. 0.707 is just saying that 70.7% of the variance in our miles per gallon is explained by these independent variables. Also in p-values, we have a couple non-significant p-values. So this p-value of 0.854 is saying that there's an 85.4% chance that acceleration has this relationship with miles per gallon, which is not good. We don't want to have a random relationship. Same for this 37.2, that's too high. Basically anything above 0.05, we actually want to get rid of or change. In this example, we've also done a bunch of scaling. So here we see that we min-max scaled acceleration. So what do we do if we do some scaling? Here you can see that the acceleration coefficient is negative 0.02. So what does that mean? It means that a 1 unit change in scaled acceleration leads to a negative 0.02 increase in the decrease in the miles per gallon. So how do we make sense of that in real life terms? We basically have to reverse transform. So in this case, we have our acceleration, and acceleration from before, we had it as, let's see, data here. Oops, this should have been data thin, I think. Please don't break. Okay, never mind. Let's undo that. But basically what you would have to do, especially if you min-max scale, you just have to multiply that number by the difference between min and max, because all we did here was we divided it by min and max. You just have to multiply it again and then plus the minimum value. So we would just take negative 0.02, multiply it back, and then add back the minimum, and then that's how you'll get your actual interpretable coefficient. Same for these. Here they're doing a combination of scaling and log transform. You just have to reverse that transformation, which is why I do caution against doing this at this point for this project, just because there are better ways of doing this and keeping track of this that we'll learn next phase, but just to keep in mind. Okay, so any questions about interpretation? I put all that spiel of how to interpret each of these numbers down here as well. Okay, so last time we talked a little bit about chain test split, and I think yesterday I also talked about chain test split and the whole idea of data leakage. So there's another level of validation that you can do known as cross-validation. And I'm going to illustrate why it's important to do a cross-validation with this example. And what I have here is basically I'm running 20 different linear regressions with different random chain test splits. So what I'm doing here is for I in range number, and here is 20. I am running a linear regression 20 different times and keeping track of their error. And so when I do this and save all the error values, so you can see here I'm saving the mean squared error into these lists and I'm plotting them out. You can see that there's quite a good bit of fluctuation. So if we take a look at dot describe of y, miles per gallon has a range of 9 through 46 and has a standard deviation of 8. And our training and testing error fluctuates between 9 and 12, or at least our testing error fluctuates between 9 and 12. So, and I believe this is the mean squared error. So that means not the mean squared error, it's around plus minus 3. This change in the error for each iteration is not a good thing, because what that means is our model is quite sensitive to how we do our train test split. So at one train test split, you're going to get error values of like, I don't know, about like 9.2. And at some error values, at some train test splits, you're going to get error values of like 13, or I guess in this case, like 12, which is a difference of three, I guess, square root of 3 miles per gallon, which in context is up to you to decide whether that is a large amount of error or not. But typically you don't want to see such levels of sensitivity to just different splits, because the model is not different, the features are not different. The only thing we're changing is our random split. And so therefore, something that is good to just check for is our cross-validation scores. And so what does the cross-validation score do? You feed it in a model and your X and Y, and you give it a number typically between 3 and 10. And this is known as cross-validation. So what does cross-validation mean? And we're going to use the example of CV equal to 5. Let me draw something out to illustrate. So when we do cross-validation of CV equals to 5, imagine that this is all of your data, and CV equals to 5 means that we divide our data into 5 parts, 5 equal parts. And so CV equals to 5 means that you train a model first, and then you test your model on different parts of your data. So what's happening here is this CV equals to 5 is going to take this 4 to be trained first, and then this one to be test, and see how the results are. The next time we're going to say, okay, this one is the test, and then the other 4 are the train. And they're just going to keep taking turns for each of the 5, and just to see how different are our values. So when I run this code, which is doing a 5-fold cross-validation, you can see that the numbers, you get 5 numbers returned. Here we're doing a scoring of negative mean squared error. It's negative because that's the way that scikit-learn has it. So I just take the negative of the negative and take the square root. So our absolute root mean squared error fluctuates from about 2.3 to 5.2. So our miles per gallon error fluctuates from 2.3 to 5.2, depending on how you do your split. So depending on your context in your business case, this fluctuation can be a lot, can be not a lot. So it's up to you to decide. So cross-validation score is just something that's good to check for, to just make sure that your model is not overfitting to the training data. Something else that's good to show, you can actually switch up the scoring. So here I'm scoring for negative mean squared error. You can also give it R squared. And you can see here that, yeah, there's quite a wide range of R squared here. Like, I think this is pretty crazy that just by using different parts of your data to train and test, your R squared, and in this case, ranges from 0.247 all the way to 0.83. So that's a sign of not a very good model because it is very, very sensitive to changes in the data. You can also play around with the cross-validation number. You can turn this to 10, for example, and you can see that this will basically divide into 10 different parts. R squared still changes from like 0.16 to 0.86, I think is the highest number that I see here. Yeah, 0.86. So it's quite sensitive. And maybe there are just some really, really bad outliers in this data set that are causing like the one or the couple to be not very good. So something to check. As of right now, we don't really have any methods for combating this sensitivity problem. But yeah, that's something that's coming up the next phase. If you have like a fairly solid model, you should see your results are still within context, fairly consistent.
Just a quick question. How do you, if you have multiple variables, is there a way that you can prune that out or no? If you, like if it's just one, it makes sense. But if you have like 5 or 6, how do you?
By variables, you mean features?
Sorry, say that again?
What do you mean by variables?
Like the independent variables that are going into the model. So how do you, so let's say you notice that the variation is on 1.
Oh, okay.
How are you sure that it's that one?
Got it. Okay, I think how I explained it was kind of confusing. So they're not subsetting different columns, they're subsetting different rows. If that makes sense. So I know I drew the boxes sideways, but I guess it makes more sense to draw them like up and down. So like basically each time you're doing it, you're only taking like 20% of the rows, and the features are going to remain the same.
Okay, all right.
Yeah, that was my bad. Yeah, so basically like we have roughly 400 rows here. So at each, let's see, I do CV equals to 10, meaning that for each of these, we are training on 360, testing on 40 rows. And then the columns all remain the same.
Okay.
Awesome. Any other questions?
You mentioned that we need to have 1,000 rows in our data. Is that the starting amount or the ending amount for like the final model?
I would say starting amount. If you're taking out a lot of outliers, I would say the fewer data points that you have, the more sensitive your model will be, just naturally, because it doesn't have too much data to aggregate over. I say 1,000 to start, just so you have like a good number of rows. But if you end up cutting out a lot of your rows, and if you have good justification for that, and you end up with, let's say, only 500 rows that you're running your model on, then that's fine. I wouldn't make a big deal of it.
Gotcha. Thank you.
You're welcome. Anything else? All right, so kind of similar to why we do cross-validation, we're going to talk about the bias variance trade-off. And the bias variance trade-off is a very conceptual thing, and also it's a very, very common data science interview question. And they literally ask you, what is the bias variance trade-off? So quick explanation. Bias, I like to liken to underfitting, and variance, I liken to overfitting. So bias or underfitting happens basically when a model cannot learn the training data, nor it can generalize new data. So in this example, you can see that this is an underfitted data set, or an underfitted model, sorry. So bias does arise when wrong assumptions are made, when you're like missing interaction effects. We'll talk about interactions right after this, or if we don't catch a certain kind of relationship. So therefore, our algorithm will miss relevant information, and therefore not fit our data very well. Now, overfitting happens when the model learns the training data too well, to a point where it's not generalizable to new data. And variance arises when a model is too sensitive to small fluctuations in the training set. So when variance is high, random noise can be modeled, and rather than the intended outputs, and therefore it's overfit. So in this example, where we see that, okay, at some point we get an R2 of 0.16, it's likely that this model was overfit to maybe something that was in these parts of the train test split. And there are some either outliers or some patterns that were not accounted for in this set of data. So this bias variance trade-off, I would say when one very, very clear sign of overfitting is when your training scores are low and your testing scores are high. I'm going to talk about this during our next office hour, so don't worry too much about this. I would say for now, you all just focus on like your EDA leading up to modeling. But yeah, I'm going to go through more intricate processes over our office hours. I think that will be helpful because I know we've gotten a lot of information thrown at us over the past couple of weeks. But anyways, yeah, so that's an example of potential overfitting. Basically, finding a good balance between over and underfitting is a huge challenge for data scientists, especially when you're trying to model data over a very wide range. So for example, in our housing data set, we do have houses from, I think the price range is around like 70K to like 7 million. Now, if we're using the entire data set, that means we're building a model that can predict housing prices from 70K to 7 million. And they all have linear relationships with all of the features that we're using. So that means square footage, things like whether, how many bedrooms, how many bathrooms, things like that. They're all, the assumption is that they are linearly related to the price of the house throughout the entire range. And so just keep in mind that you're making that assumption that you have the potential to over or underfit to parts of your data. I'll talk more about this during an office hour in the context of our projects, but yeah, just a good concept to just be aware of, that there is over and underfitting that can occur. Overfitting, again, you'll see big discrepancies between your train and your test metrics. But for underfitting, you just have bad results across the board because your model is just not learning anything. Okay, the next couple of sections are basically things that you can include in your project, in your linear model, as basically things that you can try out. So the first one is interactions, and the second one is polynomial terms. So the idea of interactions, very simply put, is feature engineering. And you're just making new features that are a product of existing features. That's an interaction. And there are two ways to go about it. One, if you have certain hypotheses of, okay, let's just say that square footage and number of bedrooms don't really look very linearly related to price. However, maybe if I multiply the two together, that resulting column might be more linearly related together. And that's something that is pretty hard to conceptualize like without trying it out. So that's something that you can definitely do if you have some hypotheses. Run like some scatter plots of looking at price versus bedrooms times square footage, for example. And if you really want to check out to see, so yeah, that's one way to do it if you have hypotheses. And another way of doing it, which is actually the method that's run through in your labs, is by making interaction terms for all of your features and then culling them after the fact. So I'm going to walk through the exploration of hypotheses today. So in this example, we want to look to see if there is a potential interaction between the age of or the model year of a car and its horsepower. So one way that we can do that is we can segment our data. So let's just first segment our data on one of the features. And in that case, I'm just picking to segment out the age of the car. So I'm segmenting my data for older cars and newer cars. So here I have my old cars, my new cars. This is irrelevant for now. Okay, so one way that you can see if there's a potential interaction is to explore the linear relationship between those variables and the target. So first, I'm going to run these two regressions. I'm instantiating two linear regressions, and this is using scikit-learn. Instantiating two regressions here, and I'm fitting the horsepower with only the older cars and the horsepower with the younger cars. And then when I'm getting the coefficients, I basically see that they have two different coefficients. So what that means is the relationship between horsepower and miles per gallon for different subsets of years or ages of cars, there's a different relationship between horsepower and miles per gallon. This is basically saying that with every one increase in horsepower for a younger car, miles per gallon goes down by 21. But for an older car, it actually goes down, sorry, a younger car, it goes down by 35, an older car, it goes down by 21. So this difference in relationship is a sign that maybe you want to introduce an interaction term. This, I think, shows it a little bit better. So here we have horsepower versus miles per gallon. The blue dots are the older cars, the young dots are the younger cars. So these are basically the two regressions that we ran. And you can see that there are different relationships between the two subsets. And that is a sign that maybe try an interaction term. So let's just start with a baseline just so that we can compare our results. This baseline is telling us that, and here what I'm doing is I'm fitting a regression to our X and Y with just our regular data, and I get a baseline R squared of 0.832, just so I can compare. If I'm adding this new feature of horsepower multiplied by model year, the R squared goes up a little bit by, I think, about 3. So we're up to 0.86. If we look at this, we can see that adding the interaction term, it is significant, which is great. And then, of course, we have some other insignificant things, and that you will deal with separately. Another question that I get a lot when it comes to interaction terms is, okay, if I'm keeping horse multiplied by year, what do I do with the horsepower here and the model year here? Now, in this scenario currently, with the interaction and the two individual variables separately, they're all significant. So it is possible that there's a positive additive effect, which basically means that having all three features works better. You can definitely experiment with taking out the original horsepower and model year variables just to see if the model changes by very much, but that's kind of up to you to decide. Any questions at this point? All right. So I don't have this here, but in your labs, they outline a process of making interaction terms for all the variables, and then going through a process of culling based on p-values or something like that. So that's a process that's outlined, I think, pretty clearly in the lab. So feel free to check that out. They basically are making interaction terms for every possible pair of variables, and then checking out their p-value when you add it to your model, just to see whether it's worth keeping or not. So, and they also provide you with like a pretty nifty function that automates the process for you. Okay, so that's interaction terms. The next one I'm going to talk about is polynomial regression, which is actually kind of similar. Basically, instead of multiplying terms with each other, you're multiplying a term by itself. The idea behind that is, and I'm going to use this much simpler example instead of the miles per gallon. There's this very simple example here where, let's say I want to use temperature to predict yield. Honestly, I don't even know what yield is in this scenario, but you can see that there's already not a there's not a linear relationship between yield and temperature, right? Instead of linear relationship, the relationship looks like it's more like a curve like this. Now, you would have to have a little bit of a math background to, or if you remember like anything about like quadratic functions or anything like that, if you have the memory that a quadratic function either looks like this or looks like this, based on whether it's positive or negative, then you can say that this has a quadratic relationship. If you don't have that knowledge, and that's definitely okay, just know that whenever you see some sort of like parabolic shape, that you can definitely do something about the variable to make it more linear. So in this case, because there's like that U shape over there, you can consider adding a polynomial term of temperature squared, and that's what we're going to do. So as a baseline, we're going to do this really, really bad baseline. You can see that this is the fitted line for temperature and yield by itself. And you can see that, hold on, let me just grab this. Okay, we can see that the R squared, which is this second one over here, is 0.086. So there's a very, very poor fit. There's a really, really poor fit. Only like not even 9% of the variation in yield is explained by temperature, which is not good. And also you can see that there's a mean squared error, a square root mean squared. So root mean squared error of 0.373. And the range of yield, it ranges from 2 to 3.7. And if you have like a 3.373 error, that's about like 10% of your maximum value. So again, depending on the context of yield, that may or may not be good. But let's just try something to see whether we can make this better. What we're doing here is we're just going to add an additional column that's temperature squared. So now we have temperature as well as temperature squared. And let's just fit that regression to see how it helps. Cool. So because we have that square term, the line, it's technically a straight line, but you imagine that there's just another dimension on the x-axis, which is why it looks like a curve now. But now it does look like it's fitting our data a lot better. And then we can take a look at our mean squared error. It's now 0.215, and our R squared is almost 0.7. So just by adding that interaction term, we see a great increase from like not even 9% to almost 70% R squared. And then if we want to see our summary, we can as well. We can see that here we have our matching R squared of 0.695, as well as low p-values for all. Again, maybe it is the case that there is not a linear relationship between temperature and yield itself, but potentially it is the addition of both of these that have a linear relationship. So whether you want to keep the original one or not, it's up to you to decide. But yeah, that's polynomial regression. I do also want to show you one more thing that is related to both interactions and polynomial regressions. Is there is this library that in your labs they're going to have you use, but I think it's really interesting to see. This polynomial features code basically will automatically do the polynomial features for you. And by polynomial, they mean by not just all the interactions, but also the polynomials. So basically you tell it to what degree you want to do. So technically you can also interact 3 variables with each other. You can cube a variable too, but usually for linear regression, you stop at 2. If not, it becomes harder to interpret. But yeah, there is code that you can walk through in the labs. I think there's only like 2 labs on polynomial interactions, or yeah, 2 readings, 2 labs on Canvas. So yeah, you'll make your way through that. But yeah, this was pretty cool. It automatically selects all the pairs for you, plus the variable itself, and makes all of the interaction and polynomial terms automatically. So that's really neat. But yeah, any questions on that? I think this was just like to round off all of the regression things that we've talked about since like last week, which I know like the pacing's a little weird. But yeah, we do have like a good amount of time for this project. So I hope that, you know, we can marinate with this information for a little bit. But yeah, any questions regarding any of today's stuff?
For polynomial regression, maybe just to clarify, so it's basically squaring the values of
A feature.
the feature.
Mhm.
That's it. Or
Yeah, that's
more-
it. That's it. So you still have a linear relationship between a feature. So technically the features, yeah. You still have a linear relationship between the feature and the target. Yeah, and that's a polynomial regression.
Thank you.
Yeah. There is a distinction between, it's a polynomial feature in a linear regression. That's the technical term for it, because what makes something linear is that the fact that we can definitively say, okay, an increase in 1 unit of temperature leads to a negative 0.174 relationship decrease in yield. So that's what's linear about it. There are other models that we'll talk about next phase that don't have this linear relationship. And then those we'll talk about that later. Anything else?
Going back to the interactions, how
Yeah.
did you determine the young and old models? Was that just kind of like a arbitrary stopping point?
Completely arbitrary. I think if you also like have contextual knowledge, that can be very helpful. Maybe also looking at just maybe a histogram of your variable to see, okay, what looks like a good cutoff point. Maybe you want to look at the scatter plot between the age and miles per gallon. So that threshold of where you want to cut off is up to you as well. But you can see that we're not really using that cutoff when we create the interaction. Just the fact that there is a non-linear relationship, that you have 2 different linear relationships at 2 different segments, is a sign that you might want to try interaction.
Got it.
Mm-hmm. Cool. Anything else? All right. So just to let y'all know, Friday there are those presentations, but I will also post the recording to your Slack channel just so you can see them as well. Next week, schedule is going to be interesting. I'm actually taking some time off next week. So I will be I'll be out of office Tuesday, Thursday, Friday. I just haven't taken time off in a while. And then we'll still have our regular study group on Wednesday, but I've moved one study group to the next Saturday. So you'll see that on your calendar. But I think it's also better to space out the office hours so that we're not like just 2 days in a row having probably like working on the same things. So I think that'll be beneficial regardless. But any questions, just Slack me anyways. I'll still respond whenever I'm on my computer or on my phone. So yeah, just wanted to let you all know that if I'm less responsive on any one of those days, you'll know why. Cool. All right. Any final questions before we close out?
I haven't seen the recordings for the previous study group. So is that going to be put up soon?
They're all on the playlist. I'm pretty sure they're already on the playlist. I just haven't been posting them to Slack.
Oh,
However, On Slack, I don't know if y'all have seen. Actually, let me just reshare my Slack screen. Okay, so it's on Slack. If you click on this, oops, I'm still annotating. If you go on to, if you see this, there's now this new bookmarks bar, which is pretty interesting. So I actually added these. So you can go to our playlist. And it's open on my browser, which is not being shared, but yeah, they're all there.
All right, thank you.
Yes, sorry for not mentioning sooner. But yeah, I put my booking link there. I put this Zoom link there, just in case. I don't know, easy access.
No problem.
Yeah.
Thank you.
You're welcome. It's actually a pretty sweet new Slack thing. I think they only, yeah, they only came out, like, I found out about this yesterday, so I put this all here yesterday. All right. Well, if there's nothing else, please Slack me if you have any questions. Well, yeah, during the office hours next week, I'll put like a rundown of what I'm going to talk about at each office hour on our homeroom. So just so you know, on the, oh, one more quick thing. Let me just reshare real quick. Oh, as you can see here, the playlist has all of our videos. And then also on, oh, why am I still annotating? All right. On our, what was I going to say? Oh, on our project guidelines. If you have any like big questions that are not like time sensitive or like not like little bugs and errors, at the very bottom, there's a Q&A, which you can definitely look through. These are questions that have been collected. Past students were the ones that left the questions here, and then I would like do these answers during an office hour. So I feel like there's a good amount of questions here. Some of them I think are new as well. So I'm gonna go through these every day and like I'm gonna go through these every day and like add my answers to here. So if you have questions that you want to ask, feel free to throw them in this doc as well. Yeah. All right. Well, if there's nothing else, have a good rest of your week, everybody. Slack me if you need anything. I do have some one-on-one availability next week still. So if you need it, let me know.
Thank
Right.
you. Have a good one.
All
You're
right, thank you.
welcome. Have a good night.
Bye.
Bye, everybody.
Good night.